Okay, so I guess we got to get this party started. Um, let me scroll so everyone can kind of see what it is. So this is where we left off last time. We're proving the ratio test. Again, kind of cool little convergence test because we don't have to compare it against anything. Sort of like even when we were doing the integral test, like there was a function and we had to integrate it. I guess we didn't have to figure out what the other function was, but there was still some work to do there. Here, you just kind of take this ratio, you create a new sequence where you take the ratio of two adjacent terms in the sequence, and you determine if you take their limit. And then basically whatever that limit is, it effectively tells you whether or not the sequence is effectively mimicking a geometric series. And again, you can sort of see that here with our proof from the other day where I've underlined this and I've like, oh, this is a geometric series, right? So it allowed us to compare something to a geometric series and determine convergence. That's phenomenal. So we're only half done the proof, right? Because we've proven number one here, which is that we're absolutely convergent. And then again, in brackets, that means therefore you're convergent, right? We proved absolute convergence implies convergence. So we're going to do number two next, which is to prove that if L is strictly greater than one, then the series diverges. And again, importantly, we're not saying that it diverges absolutely, right? That's not what we're saying. We're saying it actually diverges. And it turns out it's not too hard to actually give the full divergence proof, right? It's easy to get divergence absolutely immediately, but you can also get actual divergence pretty quick. Now, number three, I'm going to leave as an exercise. So it says when L is equal to 1, the test is inconclusive. And what we mean by that is we just can't tell, right? It could converge, it could diverge. When L is equal to 1, we just don't have enough information to tell. And the way that you actually prove that is just give an example of a convergent sequence where this ratio limit is equal to 1, and then give an example, or sorry, a convergent series, and then an example of a divergent series where this is equal to 1. And it's not hard, okay? Like if you play around for it with a little bit and just try some like common series that we've already played with, there are some, right? For example, if you do 1 over k squared, I'm pretty sure that gives you L is equal to 1, right? In fact, you can just kind of see it by inspection. You get like k squared plus 1, or sorry, k plus 1 all squared in the numerator, k squared in the denominator. That thing has a limit of 1, right? So that's how you do it. So like I said, I'm not going to worry about 3. Let's finish off 2, though, just so we can see that. And then I'm going to let you come up with the examples for number 3. All right, so this is the proof of the ratio test continued. So proof continued. All right, so let's now do the case where we assume that L is strictly greater than 1. And we do the exact same thing, right? So we fix some L, like little l, that is between capital L and 1. Such that 1 is less than little l is less than L, right? And a capital N such that beyond that point, we can guarantee that the L's are all above little l, or the a n plus 1s divided by n are all bigger than little l. Such that k greater than or equal to n implies a k plus 1 over a k is bigger than little l, right? And again, the reason why we do this little l is exactly the same reason as the previous case. I can't make this inequality for capital L. That's not true. But by being clever about our epsilon bands, I can guarantee that this is true for some number smaller than L, really any number smaller than capital L. And I don't want to carry around like an L minus epsilon everywhere. That's going to be a little bit messy. I want to be like, this is clearly a geometric series. So, we just use this notation instead. But again, if you want to, use your epsilon band and convince yourself that this is true, and then carry around the epsilons if you really want to. Okay, so we get that this is true. Now we do the same thing, multiply both sides by, AK. And we get that. So once again, what we're going to see here is that if we recursively sort of do the step, right, at this point, it's identical. We get this, and this thing is a geometric series. or at least it defines a geometric series, right? So it defines a geometric series with common ratio L greater than 1. And the right-hand side defines a geometric series with ratio greater than 1. So it diverges, but this is absolute divergence, but let's just kind of go through the motions anyway, and then I'll show you how we actually get divergence, right? So it's a geometric series, ratio greater than 1, so it diverges. So it diverges. And then by the BCT, we've said that this left-hand thing is bigger than the right-hand thing. The right-hand thing goes off to infinity. Basic comparison test says, therefore, the left thing does as well, right? So by the BCT, k equals 0 to infinity, an plus k diverges as well. Okay, but again, that's sort of like, that's not good enough, right? Because this is absolute divergence. And how do we know that the series isn't conditionally convergent? Well, it turns out this actually gives us something a little bit better. The fact that an plus k is bigger than L to k ak, here, let me highlight that. The fact that this is true tells us something stronger, which is enough to guarantee divergence. It tells us that the limit of these things is not 0. So, but more importantly, this is not 0, right? Because it can't be. It's bounded above by this series, and that series itself, or that, in this case, that sequence actually, the sequence on the right-hand side there, that L to the k times the absolute value of an, that thing doesn't go to 0. So even by sort of like our classic, comparison of just sequences, not even series, if the right-hand side goes off to infinity, the left-hand side must as well, right? We prove something like that for functions in like test 2 or something, right? Like you had two functions, f, if f goes to infinity, then g must go to infinity as well, right? We prove something like that, if I recall, in term test 2. And you can see the proof is, the proof is pretty quick, but so if you need to convince yourself, do it, but the right-hand side does not converge to 0, so neither does the left-hand side. And we do have a theorem which says, in the contrapositive, if the summons of the series don't go to 0, then the series can't converge, right? Or the series diverges. So that must mean, that series diverges. Okay, great, we knew that already. But the limit of the absolute values is equal to 0 if and only if the original sequence is equal to 0, right? And an plus k goes to 0 if and only if an plus k goes to 0. So we conclude that is not equal to 0. Thus, this series diverges. Okay, so yeah, sort of emulating the steps that we had before, we were able to get absolute divergence, but absolute divergence isn't good enough. So what we want to do is we want to make an argument that the terms, the summons of the series, doesn't actually go to 0 in the first place. And so, because they don't go to 0 absolutely, they don't go to 0 non-absolutely or originally, or whatever we want to say there, forcing the original series to diverge as well. Okay, and there we have it, we're done. Now, if you've got my book, at this point, there's something I go into, which is a bit of a rant, which really pisses me off. So if you pull out a bunch of books, because what we've just talked about here, right, the ratio test is a common test. They're going to learn it in 135 or 136, I guess. They would learn it in 132, 134. I mean, they wouldn't prove it, right? That's sort of reserved for us, but they would learn it. And so if you pull out a sort of a bunch of textbooks at random, and pull up their statement of the ratio test, their statement might be different. So let me go back there and kind of point that out. Okay, so the way they might state the ratio test is instead of letting AN be an arbitrary sequence and then taking the limit of the absolute values, they'll say, let AN be a positive sequence or a non-negative sequence, right? But it should be positive because we're going to divide it by AN. So they'll say, let AN be a positive sequence and then prove the theorem. And the statement of the theorem is basically the same, except instead of saying absolutely convergent, they just say convergent. Exactly. This is what I call the baby ratio test. And the proof is identical. Okay. The proof is exactly the same. It's just you take out all the absolute values everywhere. And on the surface, you might say, well, okay, well, that seems like it's basically the same statement, right? Because then if I want to, if I want to show something converges and I don't know that all my terms are positive, why don't I just take their absolute value, right? And you take their absolute value, you then apply the quote unquote baby ratio test. If you get convergence, great, you win. But the baby ratio test is strictly weaker, and it's strictly weaker because the baby ratio test does not give you divergence, right? If you use the baby ratio test, again, where you assume that the ANs are all just strictly positive, you don't do anything with absolute values. And you know that if L is greater than 1, then your series diverges. Now, if you're given a sequence where the terms aren't all positive and you take their absolute values, the best you can do is guarantee that you diverge absolutely. You're not given divergence, right? So the baby ratio test is strictly weaker because you cannot get divergence from the baby ratio test if your sequence is not already positive, okay? So this is maddening. And when you pull open, so when I was writing the book, I was like, okay, this is weird. Because I swear I've seen it stated the other way. Like, why would people deliberately state something that's weaker, right? So you open Stewart, you open like Slash-Hill-Ekin, you open, Thomas, like you just go and you open the books. And I had, at the time I was in grad school, so I had all my friends pull out all the calc books we have. We must have had like 12, 15 calc textbooks, something along these lines. And we opened them up and we found the ratio test. And it was almost exactly 50-50, right? It was like, 5 to 7 or 6 to 8 or something like this. Is that almost half of them stated the ratio test the way I've stated and half of them stated it the other way. And we couldn't, for the life of us, figure it out. Like, why would you do it this way? And the only reason to not state, right? Again, if the proofs are the same, but the result of one is strictly stronger, why wouldn't you state the stronger theorem? The only reason we could come up with is if you don't cover absolute convergence first, right? Like alternating series, conditional convergence, absolute convergence, and that sort of stuff. So if you don't do that first, you can't do this test, right? Because you can't say the word absolutely convergent. Okay, fine. I mean, you could kind of, like, you're not proving those things anyway. Why not just state the theorem and say the word convergent, whatever. So I guess that was one reason, but again, doesn't it like say something? I think actually too, one thing that I want to check is I want to go back and look at all the versions of Stewart and see, because you know how when publishers publish a new version of a book, they just artificially move sections around in order to make it so that you have to buy a new textbook because they're jerks like that. What I wonder actually is if in those books they state the ratio test correctly, and then they switch the ratio test and alternating series, and then dumb down the ratio test as just like an artificial way of moving those two sections and screwing over students. So I suspect that might be true. I don't have any hard evidence of that yet, but I suspect that that is a true thing, because otherwise, why would you do this, right? Like, why would you state a weaker theorem? I don't know. I don't understand it. Okay, so something just to be aware of. There's a lot of inconsistency with this in calc textbooks. And like I said, I really can't tell you why, because this is maddening to me. It's such a weird thing. Okay. So anyway, a kind of rant aside, why is this useful? Well, it turns out there's a lot of series. What example was I going to do? There's a lot of series that fall right away to the ratio test. And like I said, we're going to use the ratio test just a whole bunch in the next couple of weeks. Okay, it really is the most important test. So you want to get comfortable with it because it's so important. All right, so let's determine if this series, where do I need to start this series? We can start it at 0. Okay, so that's a factorial sign. Okay, so we want to determine if this converges. Now, this is a little bit tricky. Certainly, if we stare at this, the integral test is not a good test here, right? The k factorial there means we can't really compare this to a normal function. You certainly don't want to integrate the gamma function, even if you know what it is, right? So, okay, whatever. This is tricky. So integral test not going to work. Maybe we could limit comparison it, but to what? Like it's already fairly straightforward. So probably not limit. Basic comparison, it's not clear. Because we can't just do 1 over k factorial or 4 to the k or something like that. Like there's a k in both the numerator and denominator, and both of these terms are growing quickly, right? So it's really, really not clear who's winning in this fight. Like is 4 to the k winning? Is k factorial going to win? Who's going to win this fight? It's not clear. Right? So the ratio test, though, will make this very clear very quickly. All right, so let's use the ratio test. So let's set a n to be, well, let's use k. So ak is equal to 4 to the k over k factorial. And then we're going to take a limit of ak plus 1 over ak. Let's just do that. Limit as k goes to infinity of the absolute value. Okay, let me put that in just to be proper. But of course, everything here is positive already, right? So we're not worried about that. K goes to infinity. All right, so when we do this, what are we going to get? So we're going to get 4k plus 1 divided by k plus 1 factorial. And this is sort of the trick that you're looking for here when you're trying to decide whether or not you want to use the ratio test. When you do this sort of ratio, are you going to get just a ton of cancellations, right? Like that's sort of what you're looking for here is just a ton of cancellations. And the answer is yes. Yes, we are. Let me just double check something here because I feel like, oh yeah, okay, whatever. So we get that thing, right? That then converges to 0. There's no k's in the top anymore. That converges to 0. So by the ratio test, this thing is less than 1. So, we converge. So to me, that's a pretty slick thing, right? Like that was actually pretty quick and pretty easy. And also we learned something about this while we're at it. And the thing, yeah, right? Like that's really slick. It's really, really fast. And the thing that we learn as well is, the fact that this limit here is 0 really does say that k factorial actually grows significantly faster than 4 to the power of k, right? Like this thing converges. That means not only that the summing goes to 0, but the fact that when we did this, limit, the fact that we got 0, okay, because if you get any other number, it says that these two things sort of have a common ratio. But if the limit is 0, then one of those things is actually growing way faster than the other one. And in this case, k factorial is definitely growing way faster than 4 to the power of k. Okay, so an interesting one. Oh man, I'm trying to remember what it is. If you want to do a really fun example on your own, I'd maybe do this one. Let's see if I remember it. So maybe let me say this is an exercise. So maybe try doing this one. So k goes to 0 to infinity. Let's do a to the k, just for some sort of generic a, times k to the k all over k factorial. I think this is what I want. Okay, so try this one. Or maybe let's say determine the values of a for which this converges. And there's a very, assuming that I've set this up correctly and I remembered the series, there is a very surprising answer, right? So there's going to be a point. Basically, there's a point at which it converges and which it diverges. Like this, I'm just, as a spoiler, this doesn't converge for all A and it doesn't diverge for all A. There is a point, there's a hard point. It's sort of like a p-test. It's like if A is bigger than this number, then it diverges. And if A is less than this number, then it converges. And that number is not 1. So what that number is, like, so if you go and you do this calculation and you get this number, you're like, whoa, that's kind of surprising that showed up. And again, if you look at this here, now it's really not certain which of these is growing faster. We said k factorial is going to grow faster than 4 to the k, really a to the k for any a. But what about k to the k, right? K to the k is a different beast. K to the k grows really quick because you're not just exponentiating, a fixed base to a power of k, you're increasing the base as well. And it turns out, these things roughly, like this number that you're going to get, it represents the threshold of when a to the k, k to the k. Turns out you need that extra little push from the a to the k. But if you combine that numerator and then you look at the denominator, they grow at roughly the same speed. And the a is actually, your little tuner dial that decides whether you grow slower than k factorial or whether you grow faster than k factorial. So this is a really neat little exercise. I recommend that you try it. Ratio test is the way to go. You'll get sort of like a nasty limit. We didn't really talk about how to do those limits. Some of you might know from high school, but if you don't know, I don't mind if you look up how to evaluate that limit. But give it a shot. This is a really fun example. Again, assuming that I wrote it down here correctly. If you all come back to me later and are like, yeah, that example doesn't make sense, then I'll look it up for real. Okay. So there are lots of tests. We're only going to do one more. There's a ton of really exotic tests, just like there are a ton of exotic integration techniques. We're not worried about most of them. So we're just going to do one more. And this one's called the root test. Okay. So the root test, same sort of story, just assume AN is a sequence. And then what we're going to do, so same sort of story, we're going to take a limit as k goes to infinity, but this time we're going to take this thing. Okay. So we're not taking, a ratio. We're not looking at consecutive terms. We're really just looking at the terms of the sequence, at least in absolute value. And then we're taking their kth roots, right? So if you want to write this instead of as a kth root, because that's why it's called the root test, right? So we're taking the kth root of the kth term. And again, really think about that, right? We're taking the 10th root of A10. We're taking the 11th root of A11, the 12th root of A12. And we're asking, does that thing converge, right? And then if it does, then we get exactly the same statement in terms of this L. We get exactly the same statement as the ratio test. So it's easy to remember. So if 0 is less than or equal to L is less than 1, then AK converges absolutely. Absolutely. 2, if L is bigger than 1, then the series diverges. Right? And then 3, if L is equal to 1, it's inconclusive. Okay, now the proof is almost identical as well. In fact, the proof might be, to some extent, even easier. So what I'm going to do is I'll prove the convergence portion, right? So I'll prove the first case 0 is less than equal to L is less than 1. And then what I'm going to do is I'll let you prove the divergence. But you'll see when I prove convergence, it's pretty much the exact same. And then from there, again, divergence is going to be the same as that of the ratio test. So there isn't that much to do. So I'll prove convergence just to show you that they are basically the same proof. Okay, so Let's do this case. 0 is less than or equal to L is less than 1. So again, we know that the limit converges to something less than 1. So let's choose a little l, which is between L and 1, capital L and 1. So choose some L in R such that and a natural number, right? So you can see so far exactly the same. Such that, what do I want? So now we're dealing with this thing. And what do I want is less than L, right? And lo and behold, this is is even easier, right? Like we don't have to do anything tricky. If I take kth powers on both sides, boom, you now get, you don't even have like this an term hanging around. You just directly have that this thing is a geometric series, right? Just straight up directly. Now it starts in a weird place. So with the ratio test, we knew that every term after capital N was, a power of L. This geometric series starts at L to the L to the capital N. So in that sense, it might be a little bit weirder, but we sort of get there immediately, right? So equivalently, what we might want to say here is, is there more to say here? If I rewrite this in terms of N to the K, it is what it is, right? So again, this is a geometric series. So this defines a geometric series. With ratio less than 1. Right, so by the BCT, again, the best that we can sort of do is guarantee that this series converges. But of course, again, if that series converges, so does the original one, right? And this implies that the sum from k equals 0 to infinity, AK converges. And that's what we wanted to prove, right? We wanted to prove that it converged absolutely. So the case greater than 1 is exactly the same sort of thing. You can imagine what's going to change. Sure, you're going to change what the definition of little l is. But the only other thing that's sort of going to flip is this inequality here, right? You're going to get that this is bigger than L to the K. And then little l is going to be bigger than 1. So yeah, this thing doesn't go to 0. Therefore, the series diverges, not just absolutely, but actually diverges, right? Like it's literally the same proof. You just flip the inequality and you know now that little l is less than 1 and you're done. Okay, so I think that test is in some sense actually even easier, which is really, really nice. And in your next assignment, which I have posted, I know it's not the one you're worried about right now, but your next one is up. And what I'm going to have you do is prove that even though, surprisingly though, even though this test is easier to prove, this test implies the ratio test, right? Like basically any test, which direction would this go? Yeah, so if you converge or diverge if the ratio test is successful on you, then the root test will also be successful, but the opposite is not true. So there are some series where the root test works and you will get a non-inconclusive thing, right? Like that's what we mean by working, is that your answer is not inconclusive. So if it works for the ratio test, it'll work for the root test, okay? So anything which the ratio test can do, the root test can also do. But there are some things that work for the root test that don't work for the ratio test. All right, so the root test is strictly stronger. And so in that case, you might be tempted just to universally apply the root test, right? You may be like, this is a stronger theorem. Why would I use it? Well, when you prove that anything which works for the ratio test will also work in the root test, it's a little bit complicated. It's actually not super, like the math to show that that works out is relatively complicated. So in practice, it can be easier just to directly apply the ratio test, like the math kind of falls apart quicker, as we saw in that previous example, right? The math is quick and sort of easy to do. Whereas if you plugged it into the root test, the math can actually get messy because you're taking kth roots, right? Which is kind of a weird thing to do. So in theory, you could always apply the root test and probably know that you were safe. In practice, the ratio test is actually going to be useful more often. It's one of these weird examples of this is a stronger theorem, but in practice is much less practical. Okay. And then let's do a quick and dirty example, and then we'll be done for the day. Because I do not want to start the next stuff. So determine if this thing, can I start at 0? Yes, I can. I'll start at 0. Infinity, k to the k. Converges. Okay. And again, when your thought process, when you look at something like this, your thought process should basically be, okay, look at that denominator. You've got e to the k plus k. The plus k is useless, right? It's not really contributing anything. As k gets really, really big, the things that are going to be important are k to the k and e to the k. So I'm going to limit comparison test the plus k away because it's not really significant. Then once I've done that, what's left over? K to the k over e to the k. Well, everything in there is raised to a power of k. So now this seems like this is a good time to apply the root test because the root test will make those powers of k vanish, right? And that's sort of the nice thing that will happen there. So that's going to be our procedure. Let's limit comparison away, the plus k in the denominator, and then let's use the root test and see if we can, and then we basically get this chain of implications about, if and only if this thing converges, if and only if this thing converges, if and only if this thing converges. So that's our goal. Like when I look at this, that's what I'm thinking. Right? Okay, so let's say let AK equal k to the k over e to the k plus k. And BK is just going to be k to the k over e to the k. So I'm going to limit comparison these to show that A's, the series in A converges if and only if the series in B converges. So applying the LCT. Right, so in that case, we're going to take a limit of AK over BK. And we'll see very quickly, things sort of work out nicely. So what is this going to be? So this is k to the k, e to the k plus k, e to the k, k to the k. So the k to the k is just going to cancel each other out. So we're going to get e to the k, e to the k plus k. And now, even though these aren't, usually when we do this with rational polynomials. But again, we can do the same sort of trick where we, multiply and divide by 1 over e to the k. Of course, that's e to the negative k if you want to write it like that. So we get 1 over 1 plus k over e to the k. And if you want to, you can convince yourself k over e to the k goes to 0, use L'Hopital. It's one application of L'Hopital. We'll show you this thing vanishes. So you get 1. Great. So by limit comparison, AKs converge if and only if the BKs converge, right? So thus, AK converges if and only if BK converges. Okay, great. So we've reduced our problem. We've got rid of that pesky little plus k in the denominator. So now let's show that BK converges. And for that, let's use the root test. So we'll show that, or we'll show, because I think this actually this one doesn't converge. So we'll check convergence on BK. Well, let's use the series. Using the root test. Okay, So again, we're going to take a limit of the kth roots of the absolute value of bk, though in this case, again, everything's positive, so the absolute value really isn't important. Right, like so. Let me rewrite that. So 1 over k, like that. So we plug everything in. Again, we're going to just drop that absolute value because we know everything is positive. So what do we get here? What was bk again? K to the k? Like that. Okay. Oh, I guess I didn't make this clear. Oh, I lied a little bit. Okay, hold on, everyone. I'm going to scroll up a little bit. Go back to the root test. I don't remember if I did this in the ratio test. I actually don't care if this exists. And I'm going to say if L is greater than 1, and here also including L is equal to infinity. Okay, so if L is equal to infinity, this still works, right? Because think about how the proof would go. You just need to show that there's some number, again, between 1 and L, right? And in this case, L is infinity. So literally you just choose little l to be any number bigger than 1, and then say, yeah, eventually all the elements of your sequence are above that, so it still works, right? So if L is equal to infinity, the theorem still works here. I don't remember if I said that for the ratio test. Did I say that for the ratio test? It's true for the ratio test as well. I did not say that. So take a second. I'll give you a second here to go do that. Go back and plug those in as well, just so you know that L equals infinity is fine. Okay, so I'm going to hold on a second here just to give you a chance to go fix your notes there if you're taking them. And then I'll carry this on. And again, like if you're not 100% convinced about that, just walk through the proof again and convince yourself like, oh yeah, I don't actually need the value of capital L anywhere in the divergence proof, right? I just need to be able to guarantee that I can find some number little l, which is bigger than 1, and that all elements of the sequence are eventually bigger than that. But that's practically the definition of what it means for your limit to go to infinity, right? Is that eventually all of your elements will be above some point, say little l. Right? So that's very, very nice. Okay, so I'll give you a couple more seconds to go, pencil in those changes, just because I don't want you to fall behind. But I mean, this example is basically done. Okay, does anyone still need time? Everyone's good? All right, nobody yelled, so I assume it's fine. So this limit here is equal to infinity. And again, this is sort of what we expected. Look at bk here, the definition at the top of the screen. They're both the same, right? We've got k to the k in the numerator. We've got e to the k in the denominator. Clearly, the numerator is growing faster, right? Because the denominator has a static base, right? It's just e to the k. The numerator has a dynamic base. It's growing as k grows. So like, again, you look at this and you're like, clearly the denominator is getting bigger. We're going to be in trouble here. And again, just like I was saying, if you do this root test or ratio test and you get 0, it means your denominator was growing way faster than your numerator. Here, if you get infinity, it's the opposite, right? Your numerator is growing way faster than your denominator. So you can kind of like take that, as sort of being like this, again, this relative growth thing that you've, come to understand. Like we're not going to talk about big O and little o. If you do CS, you can talk about that sort of stuff. But, having a good intuition for how quickly things grow is nice. Anyway, this is equal to infinity. Therefore, the bk diverges. bk diverges. So that tells us that our original thing diverges as well. And we're done. Okay, and from the root test, we also get something nice, which is if I actually took 1 over those terms, the summons, right? So if I did e to the k plus k over k to the k, so I flipped the numerator and the denominator, I would have gotten convergence, right? Like I would have for sure gotten convergence in that case because the math here is going to be the same. The limit comparison test isn't going to change. It's basically identical. And then the only thing that's going to change for the root test is that I'm going to get e over k, right? Like when I get to this step right here, I'll have the e on top of the k on the bottom, and that will be 0. And then the root test will tell me that it actually converges, right? So if I took the reciprocal of this thing, I would actually get convergence. And generally, you can sort of see from the root and ratio test, that's going to be true, right? Like if you have some sort of limit, like you take your root test, you do your ratio test, you get a limit of 2, then if you reciprocate everything, fundamentally nothing's going to change, but that limit is now going to become a half when you take the root or take the ratio, and suddenly now it does converge, right? So we do sort of get this nice, if you take the reciprocals of a divergent series, you're going to get a convergent series, as long as the root ratio tests were the things that gave you that convergence, right? So that's kind of nice. And yeah, I think we're going to stop there. Now, again, if you guys want lots of examples, so there are some, there are examples in the book, whether you've pulled up Spivak or my copy of the book, but root and ratio tests are themselves, and integral tests, frankly. These are tests that are used in like MAT156, in like a standard calculus course. So there is no shortage of examples of these sorts of problems in the world, right? You can go to Google and you can look up like, ratio test worksheet or something like that, and it will give you a million of them that you can practice. And so you should feel free to do that. Like don't, there are certainly some things that are MAT157 only that you will have a hard time finding online, like practice. This is not one of them, right? And this, frankly, this will be the last time that happens. There's only a couple of weeks left in course, but what we're about to do for the rest of the course is hard enough that 136 students don't even come near it, really. There will be pockets of 136 throughout, but so I'll tell you when those happen. Yeah, we're going to finish there. Now, next week, things are going to get hairy. So next week, what we're going to do, so far, think about what we've been doing. We've been doing sequences and series of real numbers, right? What we're going to do is we're going to switch, and we're going to start doing sequences and series of functions, okay? So next week, what we're looking at is you're going to have functions, and we're going to take a sequence of functions, and we're going to ask what it means for those to converge. And the answer is there's multiple ways that they can converge, right? And it's called uniform convergence and pointwise convergence, and we need to be able to distinguish between those things. And then we're going to make it worse, and we're going to start talking about series of functions. Right? And that's the next step. Now, you can imagine this stuff's going to get a little bit more complicated because it's not trivial when you just deal with numbers, right? Let alone when you start dealing with functions. So things are going to get a little bit tougher. The results get a little bit tougher. The proofs get a little bit tougher. But this is where we start to get the really cool stuff is going to start to happen. Okay, and then this will eventually lead us to Taylor series, which I know that some of you, have had an idea about, have sort of like heard about or learned about a little bit in the future. But that's what a Taylor series is, right? It's a series of functions, of polynomials, in fact. So that's going to lead us into Taylor series, and then we'll be in a good position where we can kind of go from there. But there's still a couple of things we've got to do. So this is what we're looking forward to next week. Root and ratio tests, surprisingly, will still apply, like not in the way that you might think that it will, but so we will actually still have to use root and ratio tests and stuff like that, okay? I would also recommend that you just start playing around with functions right now, like just play around with sequences of functions, do things, do easy things, and just go into Desmos and like plot this or something. right? For different values of n. And you can probably guess what this function is going to do, right? As n goes to infinity, this thing looks sort of like a V shape, right? But as n goes to infinity, this just becomes the straight line constant, n is equal to 1. And a good little exercise here, if you really want to play with it, is to try and figure out what it means for these sequences to converge, this sequence of functions to converge to the function, which is just the constant 1. See if you can figure out what that's supposed to do, right? Like, do you just do it for every point? Is there some sort of stronger way that you can do it? These sorts of things. That's just, I think when you start talking about sequences of functions, it's more intimidating at the beginning than it has to be. Here's another really interesting one. This is a super important example. What do I want here? I think I just want x to the n. Okay, I really like this. Should not be scary. Actually, here, let me give you a domain for this, because okay, those are nice, easy functions, right? There's nothing freaky about those functions. It's x squared, x cubed, x to the 4, x to the 5, x to the 6, blah, 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 right? Like, we're very comfortable with those. But the domain is only 0, 1, and this is important. What I want you to do, go into Desmos, plot that, right? You can have Desmos set up a little slider for you where you can just change the values of n, so you don't have to like backspace, change the number of n. Specifically, you can just move a slider around. And what I want you to do is look at what this thing is doing and try and guess what function this converges to, because you're going to be surprised. It does some weird stuff. Even though these are really nice functions, these do some really weird things. Okay, so try that and then see like, oh, we're going to be in trouble here because this is not converged to what I think it should converge to. Okay. All right, that'll do it for today then. Yeah, I don't think we've got anything else. Sure, here, actually, you know what? I can probably try to do this. And then just do it. I can send it to you. And then let's change this step. Let's start at maybe 1. And let's go to 20 step by 1. So let's see. Yeah, okay, here. So I've basically done it. So let me just share it with you. I'm going to put this in the Zoom. I've got like 2 hours between this and my next class. So I got 2 hours. So there you go. Click that. Okay, and move your slider around. And you can change that slider too, right? So you can make that slider go up to like 100 or something. And I want you to try and tell me like what function, right? Do you see this? If you're moving that slider around, maybe make the slider go to 100, right? Like edit the slider, make it go to 100. Yeah, yeah, sure, y equals x. But what function is this doing? Notice this function looks like it's, as you let n get really, really big, it stays at 0 for longer, right? And because we know that if you take like 1/2 to the power of 1,000, that's actually a really small number, right? Versus 1/2 to the power of 2 is not as small, right? 1/4 is not nearly as bad as 1/2 to the 1,000. So this function looks like it's getting closer and closer to 0. However, every single one of these functions passes through the point 1, right? So what you see is that every single one of these functions goes whoosh, and then shoots up to 1 really insanely quickly, right? Like as it starts to get close to 1, it just shoots up. So if you were to let n go to infinity, right? If you were to take this behavior to its absolute limit, well, I mean, 1 has to go to, like, it still has to pass through 1, right? Whatever this function is, all of these functions are equal to 1 at 1. So whatever the limit is, that has to be true as well. But then it looks like those functions are becoming 0 for everything else. Do you know what I'm saying? So like, that's weird. Because we now have, is there something to say about the integral? Right, okay, yeah, so that would be the next thing to say is like, what can we say about the integral of these things? So I mean, we don't want to get too far ahead of ourselves. It turns out integrals will be nice. It does seem kind of Dirac-like, except Dirac would like shoot off to infinity, right? But there's a couple of things that I want to point out here immediately, very quickly. One is these functions are all continuous, but it looks like they converge to something which is not continuous, right? These functions are all differentiable, but they converge to something which is not differentiable. So it seems like convergence, like the naive version of convergence that we're going to have from this, does not preserve the properties of our functions, right? So continuity is not preserved and differentiability is not preserved. And then, the next question is, what about integrability and what about the integral? Is that converged? Is that preserved as well? So yeah, something to think about, something kind of weird going on here. But like I said, you can play with this ahead of time and just see like how much you can sort of develop on your own. And then we'll, touch it rigorously next week. All right. So that's what we're going to do. Have a good weekend, everyone. Happy St. Patrick's Day. And I will see you Monday or Tuesday. All right. Bye, everyone. Thank you. You too, Nicole. All right, ciao, everyone. I'm going to kill the meeting here.